My name is Sintakhabalam, and this was the paper you can watch here of October, November 20, paper 42. It's A levels structured paper. For question number 1, define gravitational potential at a point. So to define the gravitational potential at a point, we have already discussed about it in our topics. It's, you can say, the first simple information or the knowledge part of the question. So we just can write it as work done in bringing unit mass from infinity to that point. This word infinity is important in it, and we have to take care of this word, this symbol in it. That we always talk whenever we are talking about the potential. So potential is the concept of bringing the mass from infinity to that point. And in the case of the potential, not the gravitational potential, if it would be electrical potential, the same definition would be work done in bringing a unit charge from infinity to that point. Let's move to the next part. It says, Earth may be considered to be a uniform sphere of radius this, with its mass this concentrated at its center, because this is important to indicate in the question of any gravitational fields that the mass is a point mass. So this concentrated at its center is clearly indicating that this is a point mass, because we always apply, this is a basic condition of the gravitational law, that we should consider it as a point mass. So there is a satellite, its mass is also given, is launched from equator. It is placed in an equatorial orbit at a height of this above the Earth's surface. Calculate the change in the potential energy del EP in the gravitational potential energy of the satellite for the movement from the Earth surface to the position of the equatorial orbit. One thing is very clear, that we have to talk about the del EP, change in the potential energy. So this change in potential energy is mass multiplied by the change in the gravitational potential, phi. And you know, the gravitational potential or electrical potential is simply Gm over R. So we can get this potential and we multiply it with mass, so we get the change in the potential energy. The important thing is that this R is now changing. There's two values for the R, because you are moving from the surface of the Earth. If you consider it, this is your Earth, and there is somewhere above the equator of the Earth, there is a satellite we have to launch, and that height is also given to us. And the radius of the Earth is also given to us. So we have to change the position of the satellite. Initially, the satellite is definitely at the surface of the Earth, and we have to pick it from here and we have to launch it into that particular orbit at that particular height. So height above the Earth's surface is this, and this is given to us as this is given to us as 5.6 into 10 raised per 6 meters. So when it is at the surface of the Earth, so it is at the distance of the radius r from the center. So at this point, its potential would be considered from the center, and at this point, its potential will also be considered from the center. So the height from here and the height from here, there would be the change in the potential, and always we take the distance from the center. You know, the radius of the Earth is also given to you. Adding 5.6 and 6.4 into 10 raised per 6 gives you the total height for the satellite from the center of the Earth. So adding these two, we can get the value 5.6 plus 6.4. This gives us as 12. Okay, 12 into 10 raised power 6. This is definitely in meters, right? So for the potential, we would definitely use the mass of the satellite, and the mass of the satellite is 2.4 into 10 raised per 3 multiplied by this del phi, which would be gm. G is 6.67 into 10 raised per minus 11. And the mass of the earth, because this is the capital M, we have to use the mass of the earth, which is 6.0 into 10 raised to 24 divided by, now we have to get the two distances. First is this and the second is this, because there's a difference in the potential. So we can get it as, it can also be taken as 1.2 into 10 raised per 7 meters. Better, we can write it in that sense as well. So take it as 1.7 into 10 raised per 1.2 into 10 raised per 7, and then we can get the potential change in that potential we are getting over here, right? So initially this is 6.4 into 10 raised per 6, and subtracting out of it is 1.2 into 10 raised per 7. So this will be the change in the radius, change in the position of the satellite. So doing this calculation, we would definitely get the change in the potential energy, and doing this calculation, we'll get the value for this, and this would be no doubt 7.0 into 10 raised per 10 joules. 7.0 into 10 raised per 10 joules. Then he just gives us the second part of the same question. Determine the speed of the satellite when in the orbit. So to get the speed of any satellite in any orbit, we definitely know that if this is the Earth and around the Earth, we are having any satellite. So this is the satellite which is revolving around the Earth. It is definitely at certain distance, at certain height above the Earth's surface. So when it is revolving around the surface, definitely the force, initial force required is the centripetal force. Without centripetal force, nobody can move in a circular orbit. And you know the centripetal force is always mv square over r. R is definitely the distance from the center of the Earth to the position of the satellite, which we already have calculated 1.2 into 10 raised per 7. V is its speed and m is the mass of that satellite. Second force, which is providing this centripetal force, that is called the force of the gravitation, which is G, mass of the satellite, mass of the Earth over r square, the distance between their center square. Equating these two, we can just get the relation out of it, and that would be simply mv square divided by r becomes equals to G m over r square. Simply this m is cancelled by this m, 1r is cancelled by the square. So you get the value v square is gm over r. I can directly use this relation as well, but it's not possible for anyone to remember this relation directly. It's better to derive it all the time whenever you are going to get any orbital speed. So putting the values over here, I'll be able to find the speed. G is, constant 6.67 into 10 raised per minus 11. And mass of Earth is also 6 into 10 raised per 24 kg. And please remember, this R is the distance from the center to the position of the satellite, which we have already calculated as 1.2 into 10 raised per 7 meters. So this is 1.2 into 10 raised per 7 meters. Doing these calculations, we can get the value of the velocity. And this value of the velocity is, no doubt, is 5,800 meters per second. Okay, sir. So moving on to the next part, C part. This is little advanced part of the question. You have to give the reason over here for this. This is especially linked with the higher order skills of the question. Before the satellite in B is launched, its speed at the equator due to the Earth's rotation is this. Okay, its speed
Okay, sir.
due to the Earth's rotation is this. It's just why the energy required to launch the satellite depends upon whether the satellite in its orbit is traveling from west to east or from east to west is very important. For this, we need to get a very interesting idea that in which direction your Earth is rotating. Earth is basically rotating from west towards east. Okay, the Earth is having its rotation from west to east. If we know the rotation of the Earth is from west to east, then definitely we can have an idea that if we are launching and your satellite is also have to move in the same direction, if the launched satellite is also there and it has to continue its movement in the same direction from west to east, definitely then the energy required to launch the satellite would be lesser. That's why for this point we need to understand some very important information about the rotation of the Earth. So simply you can write over here that as we know the rotation of the Earth is from west to east. Okay, so energy required would be lesser if we launch. Energy required will be lesser if we launch the satellite in the direction west to east.